Imagine that tonight unfolds like any other. The sun slips below the horizon. Cities begin to glow with millions of lights. Across deserts, forests, mountains, and oceans, darkness slowly settles over the earth. Somewhere, children point toward the sky, waiting for the familiar silver crescent. Amateur astronomers prepare their telescopes. Sailors glance upward as they have for thousands of years. And then something impossible happens. The moon does not rise. At first, few people notice. The moon is not always visible immediately after sunset, and most of us rarely pay attention to its daily schedule. Some assume clouds have hidden it. Others think perhaps tonight is simply a new moon. But within minutes, observatories around the world begin sending urgent messages to one another. Professional telescopes sweep across the sky. Space agencies compare observations. Orbit tracking systems search every known position. There is no mistake. The moon is gone. Not hidden, not eclipsed, not shattered into fragments, simply absent. For the first time in more than 4 billion years, Earth has become a planet without its natural satellite. The news spreads faster than any event in human history. Television broadcasts interrupt their programming. Social media floods with photographs of an unusually dark sky. Astronomers struggle to explain what should be impossible. Around the world, millions of people step outside, hoping to catch even the faintest glimpse of the familiar companion that has watched over every human civilization. But there is only darkness. The stars, suddenly freed from the moon's bright glare, appear with astonishing clarity. The Milky Way stretches across the heavens like a river of pale light. Constellations, normally hidden by moonlight, become brilliant. Distant galaxies emerge, where only darkness once seemed to exist. For experienced stargazers, the sky is breathtakingly beautiful. For everyone else, it feels strangely empty. The absence is difficult to describe because the moon has always been there. Every story, every calendar, every generation of humanity has known its changing phases. It has inspired myths, guided travelers, influenced artists, and served as a silent companion to countless nights. Now, the sky feels incomplete. Yet despite the emotional shock, something remarkable is happening beneath our feet. Almost nothing. The ground does not crack open. Mountains do not collapse. Cities do not shake. There is no sudden earthquake caused by the moon's disappearance. Many people assume that removing such a massive object would trigger immediate global disaster. After all, the moon is nearly 3,500 kilometers across and weighs more than 73 quintillion kilograms. Surely losing something so enormous must tear the Earth apart. But physics tells a calmer story. Although the moon exerts a powerful gravitational influence, Earth itself remains firmly bound to the sun. Our planet's orbit around the sun depends almost entirely on the sun's immense gravity, not the moon's. The moon and Earth orbit their common center of mass together, but that shared motion is only a tiny part of Earth's journey around the solar system. As strange as it sounds, tomorrow morning the sun would still rise almost exactly where astronomers predicted. The seasons would not suddenly change. The length of the year would remain almost identical. Earth would continue circling the sun as if nothing had happened. This surprises many people because the moon appears so large in our sky. In reality, it is tiny compared with the sun's gravitational influence. The sun contains more than 99.8% of all the mass in the solar system. Its gravity governs the paths of every planet. So while the disappearance of the moon would transform life on Earth in countless ways, it would not send our planet drifting into deep space, nor would satellites suddenly begin falling. Thousands of satellites orbit Earth today, from weather observatories and communication networks to the International Space Station. Their paths are determined primarily by Earth's gravity. The moon does create subtle gravitational perturbations that engineers account for during long missions, but those effects are relatively small. Most satellites would continue orbiting normally. GPS would still function. Weather satellites would still transmit images. astronauts aboard space stations would experience no sudden jolt. Mission Control would certainly notice the moon's disappearance, but the spacecraft themselves would remain safely in orbit. Inside observatories, however, scientists would face the greatest mystery ever encountered. Every law of physics says that an object cannot simply cease to exist. There should be debris, energy, gravitational signatures, some explanation. Instead, there is only absence. Researchers would immediately test every instrument they possess. Radio telescopes would scan the heavens. Deep space probes would search nearby regions of space. Gravitational models would be recalculated again and again. The conclusion would remain unchanged. The moon is gone. Meanwhile, ordinary people begin asking practical questions. Will tomorrow be safe? Will the oceans flood? Should coastal cities evacuate? Has gravity changed enough to affect our bodies? Fortunately, the answer to that last question is reassuring. Although the moon pulls on every object on Earth, including each of us, its gravitational pull at the surface is surprisingly weak compared with Earth's own gravity. If the moon vanished instantly, your body would not feel lighter. You would not notice any physical sensation. Walking, running, breathing, and even jumping would feel exactly the same. The difference is far too small for human senses to detect directly. Yet the oceans are another story. Water responds to gravity with extraordinary sensitivity. Unlike solid rock, vast bodies of water can slowly redistribute themselves as gravitational forces change. The familiar rise and fall of the tides is the visible expression of an invisible conversation between Earth, the moon, and the sun. That conversation has just changed forever. The first hour passes quietly. The second remains calm. Cities continue their evening routines. Airplanes fly. Trains run on schedule. Children go to bed. Yet somewhere far beyond ordinary perception, every ocean on Earth has already begun responding to the missing pull of its oldest companion. The changes are almost imperceptible at first, so subtle that no one standing on a beach could recognize them with the naked eye. But hidden beneath the surface, a new rhythm is beginning to emerge. For billions of years, the moon has been the conductor of Earth's tides, gently lifting entire oceans and guiding countless ecosystems with its steady gravitational hand. Now, for the first time in the history of our planet, that conductor has fallen silent. In the hours ahead, the seas themselves will reveal just how much Earth has always depended on the quiet presence of the moon. The first night without the moon passes in uneasy silence. Across the world, observatories continue searching the empty sky, while millions of people refresh news feeds in hopes that someone will explain the impossible. Yet as dawn arrives, most cities awaken to what seems like an ordinary morning. Traffic fills the highways, markets open, fishing boats leave their harbors, schools begin their lessons. At first glance, Earth appears unchanged. But if you were standing along a quiet shoreline, watching the water with instruments precise enough to measure even the smallest differences, you would discover that the planet has already begun to respond, not with violence, not with towering waves, but with a subtle shift in one of nature's oldest rhythms. For billions of years, the oceans have risen and fallen under the combined pull of two celestial bodies. The moon has always been the dominant force, while the sun, despite its immense size, plays a supporting role because of its much greater distance from Earth. Many people are surprised to learn that the sun also creates tides. In fact, the sun's gravity is enormously stronger than the moon's in absolute terms. But tidal forces depend not only on gravity itself, but on how gravity changes across Earth's diameter. Because the moon is so much closer, its tidal influence is more than twice as powerful as the sun's. Together, these two bodies produce the familiar rhythm of high and low tides that has shaped coastlines since long before the first dinosaurs walked the Earth. Now, one of those partners is gone. The result is not the disappearance of tides altogether. Instead, Earth's oceans settle into a quieter pulse driven only by the sun. This is one of the most common misconceptions surrounding the thought experiment. Many imagine that removing the moon would cause the oceans to suddenly surge across continents or collapse into enormous basins. Neither would happen. The sea would not rush outward in a single catastrophic wave, nor would coastlines instantly move hundreds of kilometers. Water possesses tremendous inertia. Entire ocean basins cannot reorganize in a matter of minutes. Instead, the tidal bulges that once followed the moon would gradually weaken as the oceans adjusted to their new gravitational environment. Within the first day, tides would still occur, but they would be dramatically smaller, roughly one-third of their previous average height. To someone relaxing on a beach, the change might not even seem dramatic at first. The water would still move in and out. Waves would still break against the shore. Wind would still shape the surface of the sea. Yet experienced fishermen would notice something unusual almost immediately. The familiar timing of the tides no longer matches centuries of observation. Ports that relied on predictable tidal windows begin reporting unexpected conditions. Some harbors that once filled deeply twice each day now receive far less water. Certain channels become difficult to navigate. Others remain unusually calm. Around the world, shipping companies begin revising schedules that have depended on lunar tides for generations. The greatest changes appear in places where tides were once among the highest on Earth. Consider the Bay of Fundy in eastern Canada, famous for experiencing tidal ranges exceeding 16 meters in some locations. These extraordinary tides exist because the moon's gravitational pull resonates with the shape of the bay itself, amplifying the daily rise and fall of the water. Without the moon, that magnificent natural phenomenon nearly disappears. The world's most dramatic tides become modest ones. Tourists who once gathered to watch entire harbors empty and refill would instead witness only gentle changes in sea level. Similar transformations unfold across the globe. In Northern Europe, tidal flats that have appeared and disappeared for thousands of years begin changing their rhythm. Along the Atlantic coast of North America, estuaries experience weaker currents. Mangrove forests in tropical regions receive less frequent flooding. River mouths that once breathed with the ocean begin settling into an unfamiliar pattern. These changes may sound subtle, but coastal ecosystems are extraordinarily sensitive to the movement of water. Twice each day, tides transport oxygen-rich seawater into marshes and estuaries. They carry nutrients, redistribute sediments, flush pollutants, and connect countless habitats that depend upon regular flooding. Every tidal cycle is part of an enormous planetary circulation system. Now that circulation has weakened, one of the first visible consequences would appear not in the open ocean, but in wetlands. Salt marshes depend on regular inundation to maintain their delicate balance between land and sea. Many plant species have evolved to survive brief periods beneath salt water before drying again as the tide retreats. With smaller tides, some marshes would flood less often, others might gradually dry. Still others would accumulate sediments differently than they have for thousands of years. The changes would unfold slowly over months and years, but ecologists would recognize the warning signs almost immediately. Estuaries, the places where rivers meet the sea, would also begin behaving differently. Normally, incoming tides push seawater inland before rivers carry it back toward the ocean. This constant mixing creates some of the most biologically productive environments on Earth. Many juvenile fish spend their earliest months in these sheltered waters. Countless shellfish depend upon them. Migratory birds gather there in astonishing numbers. Without strong lunar tides, that mixing weakens. Layers of fresh and salt water become more stable, reducing the exchange of oxygen and nutrients that supports rich marine life. Even the movement of sand begins to change. Every coastline on Earth is shaped by a balance between waves, currents, rivers, storms, and tides. Remove one of those forces, and beaches slowly begin to evolve into new forms. Some sandbars remain exposed for longer periods. Certain barrier islands erode differently. Channels carved over thousands of years gradually shift toward new equilibrium. The changes are measured not in hours, but in seasons and decades. Yet every coastal engineer would understand that the planet has entered an entirely new geological chapter. Far offshore, another quiet transformation is beginning. Although surface waves are created mainly by wind, tides help generate powerful currents that move immense volumes of water through narrow passages and around underwater mountains. These currents stir nutrients upward from the deep ocean, feeding microscopic plankton that form the foundation of marine food webs. Without the moon's stronger tides, many of these mixing processes weaken. Nothing dramatic happens overnight. No vast regions of ocean suddenly die, but scientists monitoring ocean circulation begin recording subtle declines in vertical mixing across certain regions. It is the first hint that changes reaching far beyond the coastline are already underway. Perhaps the most remarkable aspect of this entire transformation is how quiet it is. Hollywood often imagines planetary disasters as moments of overwhelming spectacle, towering waves, collapsing cities, and instant destruction. Nature is often far more patient. The disappearance of the moon would not announce itself with a single catastrophic event. Instead, it would rewrite the operating instructions of Earth's oceans one tide at a time. For most people, life would continue almost normally during those first weeks. Yet beneath every ship crossing the sea, beneath every fishing village, every coral reef, every tidal marsh, and every river mouth, the planet would already be adjusting to the loss of a companion that had guided its waters since nearly the beginning of Earth's history. And while the oceans slowly learn a new rhythm, millions of living creatures face an even greater challenge. For many of them, the moon has never simply illuminated the night sky. It has served as a clock, a calendar, a signal for migration, reproduction, hunting, and survival. Now, for the first time in hundreds of millions of years, that ancient clock has stopped. By the end of the first week, humanity would still be trying to understand what had happened to the moon. Astronomers would continue searching the solar system for answers. Oceanographers would refine new tidal models. Governments would issue scientific briefings instead of emergency evacuations, reassuring the public that the planet itself remained stable. For most people, daily life would continue. Cars would still fill the roads. Airliners would cross the skies. Cities would glow each evening beneath an unusually brilliant canopy of stars. Yet beyond the lights of civilization, another story was quietly unfolding. Unlike humans, countless species do not merely admire the moon. They depend on it. To them, the moon is far more than a bright object in the night sky. It is a clock that has measured time with extraordinary consistency for hundreds of millions of years. Long before the first humans learned to count the days, living organisms had already evolved to recognize the moon's changing phases, its monthly cycle, and the subtle variations in moonlight that accompany each night. Now that ancient rhythm has disappeared, the effects begin almost immediately, not because animals understand that the moon is gone, but because the environmental signals they have relied upon for countless generations simply stop arriving. One of the most remarkable examples can be found beneath the warm waters of tropical oceans. Once each year, something extraordinary takes place on coral reefs around the world. For just a few nights, often shortly after a particular full moon, entire coral colonies release billions of eggs and sperm into the water almost simultaneously. Vast reefs stretching for kilometers appear to bloom beneath the sea, filling the water with drifting clouds of life. This synchronized spawning is one of the largest reproductive events on Earth. Scientists have discovered that many coral species use a combination of water temperature, day length, and lunar cycles to coordinate this remarkable event. The timing must be nearly perfect. If colonies release their reproductive cells days or even hours apart, fertilization would decline dramatically. Without the moon, that precision begins to unravel. Some corals might still respond to seasonal temperature changes. Others might rely more heavily on internal biological clocks. But across many reefs, the synchronization that has evolved over millions of years would weaken. Instead of one great pulse of reproduction, spawning might become scattered over many nights. Fewer eggs would meet sperm. Fewer larvae would survive. Coral populations, already stressed by warming oceans and pollution, would face yet another challenge. The reefs themselves would not vanish overnight, but one of nature's most elegant reproductive calendars would begin to lose its accuracy. Thousands of kilometers away, along sandy coastlines, another ancient ritual would quietly change. Female sea turtles spend years crossing entire oceans before returning to the beaches where they were born. Many species prefer nesting during darker nights, reducing the chances that predators will discover their eggs. Hatchlings, emerging weeks later, often use natural light over the ocean to help guide their first journey toward the sea. Although artificial lighting already disrupts this process in many coastal regions, the complete disappearance of the moon would create an entirely new environment. Some beaches would become darker than they have been for millions of years. Others would be illuminated only by stars. Scientists cannot say with certainty how every turtle species would adapt, but many behaviors linked to lunar brightness would almost certainly begin changing over successive generations. The moon has never been the only cue, but it has always been one of the most reliable. Along the Pacific coast of California, another remarkable creature follows an equally ancient schedule. The grunion, a small silver fish, performs one of the strangest breeding rituals in the animal kingdom. During exceptionally high tides associated with the full and new moon, female grunion ride incoming waves onto sandy beaches, bury their eggs beneath the wet sand, and return to the sea before the next wave retreats. Weeks later, another exceptionally high tide washes over the beach, triggering the eggs to hatch and carrying the young fish into the ocean. It is a life cycle synchronized with remarkable precision to the rhythm of lunar tides. Without the moon, those exceptionally high spring tides disappear. The beaches still exist. The ocean still rises and falls. But the timing and height of the tides no longer match the conditions that shaped the grunion's evolution. Their reproductive strategy would be forced to change or fail. Similar stories unfold across every continent. Horseshoe crabs, whose ancestors lived before the dinosaurs, gather on beaches during particular lunar tides to lay their eggs. Those eggs become essential food for migrating shorebirds, traveling thousands of kilometers each year. If horseshoe crab spawning changes, bird migrations may also be affected. One alteration ripples through another. Nature is full of these hidden connections. Even creatures that never approach the ocean often depend upon the moon in surprising ways. Many nocturnal predators have evolved hunting strategies based on moonlight. Owls adjust their activity depending on the brightness of the night. Some species of wildcats hunt more effectively beneath certain lunar phases. Others become less active during bright full moons because their prey can see them more easily. Rodents frequently reduce their movement on brightly lit nights to avoid predators. Insects alter their flight behavior. Spiders change when they build their webs. Even tiny plankton near the ocean's surface migrate upward and downward according to changing levels of nighttime illumination. Remove the moon, and every one of these relationships begins adjusting. Some predators suddenly enjoy darker hunting conditions every night. Others lose the visual advantages they once relied upon. Certain prey species become more active, others become more vulnerable. No single outcome applies everywhere. Each ecosystem begins finding a new balance. Perhaps the most fascinating aspect of this transformation lies inside the animals themselves. Many organisms possess biological clocks that measure far more than the familiar 24-hour cycle governed by sunlight. Scientists have identified internal rhythms synchronized with the approximately 29.5-day lunar month. These lunar clocks influence reproduction, hormone production, feeding behavior, migration, and even cellular processes in certain marine organisms. Unlike the daily circadian rhythm, these monthly cycles remain one of biology's most intriguing frontiers. Researchers are still discovering how deeply lunar timing is embedded within living systems. If the moon vanished, These internal clocks would not simply stop. At first, they would continue running according to inherited rhythms, but without regular environmental cues to reset them, many would gradually drift out of synchronization. Imagine an orchestra performing without its conductor. Each musician continues playing. Each knows the melody. Yet over time, tiny differences in timing accumulate until harmony becomes increasingly difficult to maintain. Nature has spent hundreds of millions of years tuning this orchestra. Now its oldest conductor has fallen silent. Interestingly, not every consequence would be harmful. Some nocturnal animals might benefit from permanently darker skies. Astronomers already know that artificial light has dramatically altered nighttime ecosystems. The loss of moonlight would create an environment unlike anything experienced in recent evolutionary history. Species sensitive to bright nights might expand into new territories. Others would decline. Evolution would continue doing what it has always done, favoring organisms capable of adapting to changing conditions. Life is remarkably resilient. Earth has survived asteroid impacts, supervolcanoes, ice ages, and mass extinctions. The disappearance of the moon would not end life, but it would begin rewriting countless ecological relationships that have existed since long before humanity appeared. Most of these changes would unfold gradually. Some would take decades, others centuries. Still others would require thousands of years before becoming fully apparent. Yet every altered migration, every disrupted spawning event, every changing predator-prey relationship points toward the same remarkable truth. The moon has never simply illuminated Earth's nights. It has quietly organized the schedules of life itself. And while animals struggle to adapt to the loss of their oldest calendar, another transformation is beginning far beyond the reach of any living creature. Hidden within the vast circulation of the oceans and the atmosphere, Earth's climate is preparing to enter a future unlike any it has experienced during the entire history of human civilization. By the end of the first year, the disappearance of the moon would no longer be just an astronomical mystery. It would have become a planetary experiment unfolding in real time. Scientists around the world would now possess months of observations. Coastal stations would report weaker tides. Marine biologists would be documenting unexpected changes in coral spawning and animal migrations. Shipping companies would have rewritten centuries-old tide tables. Every major observatory would still point powerful telescopes toward the place where the moon should have been. Yet another question would now rise above all the others. Would Earth's climate begin to change? For many people, the answer seems obvious. The moon influences the oceans influence the climate. Surely removing the moon must trigger immediate weather chaos. The reality, once again, is both more subtle and far more fascinating. Weather and climate are not the same thing. Weather is what happens today. Climate is the average behavior of the atmosphere and oceans over decades, centuries, and even millennia. A hurricane may last a week. A climate shift may unfold over hundreds of years. The moon's disappearance would not suddenly create endless storms or permanent winters. Instead, it would begin changing the hidden machinery that slowly regulates Earth's climate. To understand why, imagine the oceans not as still bodies of water, but as enormous engines constantly transporting heat around the globe. Warm tropical water flows toward the poles. Cold polar water sinks and eventually returns toward the equator. This immense circulation distributes solar energy, moderates temperatures, and helps make much of Earth habitable. Without these moving oceans, many regions would experience far more extreme climates. Most people are familiar with surface currents like the Gulf Stream, which helps keep Western Europe much warmer than other places at similar latitudes. But beneath the surface exists an even more complex world of slow-moving currents, vertical mixing, and deep water circulation. Some of these processes are powered primarily by differences in temperature and salinity. Others receive an important contribution from tides. Every day, tidal forces push enormous volumes of seawater through narrow channels, across underwater ridges, and over rugged mountain ranges hidden beneath the sea. As these powerful flows encounter the uneven ocean floor, they generate turbulence that mixes cold deep water with warmer surface layers. This vertical mixing may seem insignificant compared with towering ocean currents, but it plays a quiet and essential role in distributing nutrients, oxygen, and heat. Without the moon, much of that tidal energy disappears. The sun continues generating smaller tides, but the total amount of mixing declines. Nothing dramatic happens during the first year. The oceans do not suddenly stop circulating. Instead, scientists begin detecting small but measurable differences in regions where tidal mixing was once strongest. Deep waters remain slightly more isolated. Surface waters exchange less energy with the depths below. The changes are subtle enough that most people never notice them, but climate scientists understand what they represent. Earth's great ocean engine is beginning to operate under different conditions than at any point in human history. One of the first consequences may involve nutrients. Far below the surface, countless organic materials slowly sink toward the ocean floor. As they decompose, nutrients accumulate in deeper waters. Turbulent mixing eventually returns many of these nutrients to the sunlit surface, where microscopic algae, known as phytoplankton, use them to grow. These tiny organisms may be invisible to the naked eye, yet together, they produce roughly half of the oxygen we breathe. They also form the foundation of nearly every marine food web. Fish feed on smaller organisms that feed on plankton. Whales consume vast quantities of plankton directly. Entire fisheries ultimately depend upon these microscopic plants. If less nutrient-rich water reaches the surface in certain regions, biological productivity may gradually decline. Again, this is not an immediate global collapse. Some areas would experience almost no change. Others could become noticeably less productive over decades. Marine ecosystems are extraordinarily diverse, and each region would respond differently. Nature rarely follows a single universal pattern. Meanwhile, another invisible system is quietly adjusting. The oceans absorb enormous quantities of carbon dioxide from the atmosphere. This natural exchange plays a vital role in regulating Earth's climate. The movement of carbon between air, water, and living organisms depends upon countless physical and biological processes, many of which are influenced by ocean circulation. A reduction in tidal mixing does not suddenly halt Earth's carbon cycle, but it could gradually alter how efficiently carbon moves through different parts of the ocean. Scientists would likely spend decades refining climate models to understand these new conditions. Some predictions would prove correct, others would require revision. As with any unprecedented planetary event, observation would become the greatest teacher. Along coastlines, local weather patterns would also begin evolving. Tidal wetlands and estuaries act as natural buffers between land and sea. They store floodwaters, moderate temperatures, and support rich biological communities. As these environments slowly change under weaker tides, local climates may change with them. Some wetlands could shrink. Others might accumulate sediments differently. Certain coastal regions would gradually become more vulnerable to storm surges, not because storms themselves are stronger, but because natural protective landscapes have changed. Ironically, one of the greatest misconceptions about the moon concerns hurricanes. Many people assume the moon directly controls the formation of tropical cyclones. It does not. Hurricanes draw their energy primarily from warm ocean water and atmospheric conditions. Removing the moon would not suddenly create more hurricanes, nor would it eliminate them. Storms would continue forming much as they do today. The atmosphere remains driven by the unequal heating of Earth from the sun. The rotation of the planet still creates the Coriolis effect. Water still evaporates. Clouds still form. Rain still falls. Weather continues. What changes is the background upon which weather unfolds. Think of an orchestra again. Removing a single instrument does not stop the performance, but the music gradually becomes different. The moon has always been one quiet instrument within Earth's climate symphony. Its influence is rarely dramatic. Yet over centuries, those quiet notes matter. Perhaps nowhere is this more apparent than in the polar oceans. Around Antarctica and the Arctic, tidal mixing helps influence sea ice formation, ocean layering, and the movement of dense water masses that eventually become part of the global circulation system. These are among the most sensitive components of Earth's climate. Even small changes can produce effects that slowly spread throughout the world's oceans. Researchers studying these regions would almost certainly discover new behaviors never before observed. Entire fields of climate science would be rewritten. The disappearance of the moon would become one of the defining scientific events in history, not because it immediately transformed the weather, but because it offered humanity an unprecedented opportunity to observe how deeply connected Earth's systems truly are. Perhaps the greatest lesson emerging after the first year would be one of humility. Our planet often appears stable because most of its important processes unfold far too slowly for human perception. Mountains rise over millions of years. Continents drift by centimeters each year. Ocean circulation may require centuries to complete a single cycle. Climate itself often changes gradually enough that generations scarcely notice. The moon has participated in these slow processes since almost the beginning of Earth's history. Its influence has never depended upon sudden drama. Instead, it has quietly shaped the conditions that allowed life to flourish. Yet, even these climate changes, unfolding across centuries, are not the moon's greatest gift to Earth. Its most profound contribution lies hidden within the motion of the entire planet itself. For billions of years, the moon has acted as an invisible stabilizer, gently governing the orientation of Earth's axis as it spins through space. Without that steady gravitational partnership, the future of our planet becomes far less predictable. To understand why, we must leave behind the timescale of years and begin thinking in millions of years. Only then does the moon's greatest influence finally reveal itself. For the first few years after the moon's disappearance, the greatest changes have taken place along coastlines and within the oceans. Most people have adapted surprisingly well. New tide tables have replaced old ones. Marine scientists continue documenting shifts in ecosystems. Children born after the event have never seen moonlight, and to them, a sky filled only with stars feels perfectly ordinary. Human civilization moves forward, but nature is only beginning its longest response. To understand the moon's greatest influence on Earth, we must leave behind the timescale of years, centuries, and even civilizations. We must begin thinking like a planet. Imagine watching Earth from deep space, not for a single day, but for millions of years. From this distant perspective, our world is not as steady as it appears. Earth spins like a giant top, completing one rotation every 24 hours. Yet no spinning top remains perfectly upright forever. As it turns, its axis slowly wobbles. Earth behaves in much the same way. Today, our planet is tilted by about 23.5 degrees relative to the plane of its orbit around the Sun. That tilt is the reason we experience seasons. As Earth travels around the Sun, each hemisphere alternately leans toward and away from the sunlight, creating the familiar cycle of spring, summer, autumn, and winter. If Earth had no tilt at all, the seasons would almost disappear. If the tilt were much greater, seasonal contrasts would become far more extreme. The remarkable stability of Earth's tilt has been one of the quiet foundations of our planet's long-term climate, and much of that stability comes from the moon. This may be one of the least appreciated facts in planetary science. Although the moon is far smaller than Earth, its gravitational pull acts like an enormous stabilizing hand, helping keep Earth's rotational axis from wandering too dramatically over immense spans of time. It does not hold the axis perfectly still. In fact, Earth's axis slowly traces a circle in space, much like the wobble of a spinning toy top. This motion, known as axial precession, takes roughly 26,000 years to complete one cycle and has been understood by astronomers since antiquity. The moon participates in this graceful motion, gently regulating its pace. But what happens if that stabilizing influence suddenly disappears? Computer simulations developed over the past several decades offer a fascinating answer. Without the moon, Earth's axial tilt would likely become far less predictable over millions of years. Instead of remaining within a relatively modest range, the tilt could drift through much larger variations as the gravitational influences of the Sun and the other planets slowly reshape Earth's orientation. Unlike the disappearance of tides, which would be noticed within days, this transformation would unfold so gradually that countless generations would pass before its consequences became obvious. Yet over geological time, the effects could be profound. Imagine a future in which Earth's tilt gradually increases to 40 degrees. Summers at high latitudes would become dramatically warmer. Regions near the Arctic Circle could experience months of intense sunlight far stronger than today. Winters, however, would become darker and colder than modern experience. Snow and ice would melt rapidly during one part of the year, only to return with extraordinary severity during another. Now imagine the opposite. Suppose Earth's tilt gradually decreased toward 10 degrees. Seasonal contrasts would weaken. Many regions would experience climates that changed little throughout the year. Rainfall patterns would slowly reorganize. Vegetation zones would migrate. Entire ecosystems would begin evolving under conditions unlike those known throughout most of human history. Neither scenario would occur overnight, nor is either guaranteed. The exact evolution of Earth's tilt without the moon remains an active area of scientific research. Computer models produce different possibilities depending on assumptions about planetary interactions over immense timescales. What scientists agree upon is the broader conclusion. The moon acts as a powerful stabilizer. Without it, Earth's long-term orientation becomes significantly less predictable. That uncertainty alone could reshape the future of life. The consequences would extend far beyond changing temperatures. Seasonal rainfall governs forests, grasslands, deserts, and agriculture. It determines when rivers flood. It influences ocean currents. It shapes migration routes. Even small long-term shifts in seasonal patterns can gradually transform entire continents. During Earth's history, relatively modest changes in orbital geometry have already contributed to the succession of ice ages and warmer interglacial periods. These slow variations, known collectively as Milankovitch cycles, alter how sunlight is distributed across the planet over tens of thousands of years. The moon does not create these cycles. Instead, it helps prevent Earth's axial tilt from wandering far beyond the ranges that have characterized recent geological history. Without that restraint, future climate cycles could become considerably more dramatic. Imagine standing where modern-day New York now lies. In one distant future, warmer summers might support forests extending far into what is today the Arctic. Millions of years later, the same location could experience long winters severe enough to encourage the expansion of continental ice sheets once again. Entire ecosystems would migrate across continents at walking speeds measured not in days, but in centuries. Species capable of adapting would survive. Others would disappear. Evolution has always followed climate, and climate follows the laws of celestial mechanics. One remarkable aspect of this story is that none of these changes require a catastrophe. There is no exploding planet, no collision, no global firestorm. Only gravity, patient, invisible gravity. Every second, every minute, every year, the gravitational dance between Earth and the Moon quietly nudges our planet towards stability. Remove one partner from that dance, and the choreography slowly changes. Astronomers often compare planetary systems throughout our galaxy. Some rocky planets may possess large moons. Many probably do not. If intelligent observers lived on those worlds, they might experience climates that fluctuate far more dramatically than ours over geological time. Some planets could remain stable enough for complex life. Others might endure environmental swings that repeatedly challenge long-term biological evolution. Earth's unusually large moon may therefore represent more than a beautiful feature of the night sky. It may be one reason our planet has enjoyed an exceptionally stable environment for hundreds of millions of years, a span long enough for dinosaurs to rise and fall, for mammals to flourish, and eventually for human civilization to emerge. Scientists continue debating exactly how essential that stability has been. Some researchers argue that life could adapt even under much larger variations in axial tilt. Others believe the moon's stabilizing influence significantly increased Earth's long-term habitability. Both perspectives acknowledge an important truth. The moon has shaped Earth's history in ways far deeper than tides alone. Even after millions of years, however, the story is still not complete. The moon has influenced not only the direction in which Earth points, but also the speed at which Earth spins. Every sunrise, every sunset, every 24-hour day that feels so natural to us is part of a much longer story, one that began when our young planet rotated far faster than it does today. Without the moon, that story would take a very different path into the future. In the next chapter of our journey, we will discover how a silent companion has been slowing Earth's rotation for billions of years, quietly shaping the rhythm of every day experienced by every living creature that has ever called this planet home. If you could watch Earth from space over the course of billions of years, one movement would become impossible to miss. The planet spins, patiently, relentlessly, day after day, year after year. Earth turns beneath the sunlight like a great blue wheel. To us, that rotation feels permanent. A day has always been 24 hours. Morning follows night. Night follows morning. It seems as fixed as the stars themselves. But in truth, Earth's rotation has never stopped changing. Every single day since the moon formed, our planet has been slowing down. Not dramatically, not enough for anyone to notice during a single lifetime, but steadily, with extraordinary consistency. The reason is one of the most elegant consequences of gravity in the solar system. It begins with the tides. Earlier, we explored how the moon raises enormous tidal bulges in Earth's oceans. Because Earth rotates much faster than the moon orbits our planet, those bulges are never perfectly aligned beneath the moon itself. Instead, Earth's rapid rotation carries the bulges slightly ahead. Imagine spinning while holding a heavy object tied by a rope. The object resists your motion, gently pulling backward as you continue to turn. Something similar happens between Earth and the moon. The tidal bulges, pulled slightly ahead of the moon's position, exert a tiny gravitational tug on the moon itself. In response, the moon pulls back on Earth. This constant exchange transfers a small amount of Earth's rotational energy into the moon's orbit. As a result, two remarkable things happen at the same time. Earth's rotation slows. The moon gradually moves farther away. Even today, astronomers can measure this process with astonishing precision. During the Apollo missions, astronauts placed special reflective mirrors on the lunar surface. By bouncing laser beams off those reflectors, scientists have measured the moon's distance to within a few centimeters. Those measurements reveal that the moon is receding from Earth by approximately 3.8 centimeters each year. About the width of a fingernail, it is an almost unimaginably slow journey. Yet over billions of years, those tiny increments accumulate. The moon was once far closer than it is today, and Earth spun far faster. Geological evidence preserved within ancient rocks tells an extraordinary story. Hundreds of millions of years ago, a day on Earth lasted only about 22 hours. Travel even farther into the past, and the rotation becomes faster still. More than a billion years ago, Earth likely completed one full rotation in less than 20 hours. Soon after the moon formed over 4 billion years ago, our young planet may have spun so rapidly that a single day lasted only 5 or 6 hours. Imagine watching the sun race across the sky 4 times faster than it does today. Morning, noon, sunset, night, all within what we now think of as half a working day. The world would have felt fundamentally different. powerful winds may have circled the globe, weather systems would have evolved under much faster rotation. The familiar rhythm of life itself would have followed an entirely different schedule. Then the moon began its quiet work. Over billions of years, tidal friction gradually converted some of Earth's rotational energy into heat within the oceans, while simultaneously pushing the moon outward. Little by little, the days grew longer. 6 hours became 10, 10 became 16, 16 became 20. Eventually, they reached the 24-hour cycle that has governed nearly all of recorded human history. This slow transformation shaped far more than astronomy. Every living organism on Earth evolved under the lengthening rhythm of the day. Plants synchronized photosynthesis with changing daylight. Animals developed internal biological clocks. Sleep cycles emerged. Predators and prey adjusted their behavior. Even the chemistry inside our cells became tuned to Earth's rotation. Now imagine that the moon suddenly disappears. Would Earth immediately begin spinning faster again? No. This is another common misunderstanding. Removing the moon would not reverse billions of years of slowing. Earth's current rotation would continue almost unchanged. Tomorrow would still contain 24 hours. Next year would as well. Even thousands of years later, the difference would remain almost impossible to detect. The change lies in the future. Without the moon, the greatest source of tidal braking vanishes. Solar tides would continue exerting a much weaker braking effect, but Earth's rotation would no longer slow at anything close to its previous rate. The 24-hour day that feels so familiar to us would become remarkably stable for immense spans of geological time. In a sense, humanity would inherit Earth's current rotation as a kind of frozen legacy. Future civilizations, living tens of millions of years from now, might still experience days very close to 24 hours long. In the universe where the moon remained, however, the story would continue. Days would slowly lengthen. Hours would gradually accumulate. The difference is almost impossible to imagine because it unfolds so slowly. A human lifetime is simply too brief. Even the rise and fall of civilizations occupy only an instant on the timescale of planetary evolution, yet planets measure time differently. To Earth, a million years is merely another page in a very long book. There is another fascinating consequence of this slowing rotation. As Earth's spin changes, the atmosphere and oceans adjust with it. Rotation influences the Coriolis effect, the invisible force that helps organize global wind patterns, ocean currents, and storm systems. A much faster spinning Earth will produce different atmospheric circulation than the one we know today. Likewise, an Earth whose rotation eventually slowed much further would also experience gradual changes in global circulation. Without the moon, that future evolution largely pauses. Earth continues spinning with remarkable consistency, while its climate evolves for other reasons. Ironically, this means that removing the moon creates two very different stories unfolding simultaneously. On one hand, Earth's axial tilt becomes less stable over millions of years, allowing greater climatic uncertainty. On the other, Earth's daily rotation becomes more stable because the primary mechanism slowing it has disappeared. One aspect of the planet grows less predictable, another becomes more constant. Nature rarely changes in only one direction. Every system influences another. Every consequence carries unexpected balances. Planetary scientists often describe Earth as a network of interacting systems rather than a collection of independent parts. The atmosphere influences the oceans. The oceans influence climate. Climate shapes ecosystems. Life alters the atmosphere. Gravity quietly governs them all. The moon has participated in this network from almost the beginning. Its influence reaches far beyond what we see in the night sky. It has quietly adjusted the pace of every sunrise ever witnessed by every creature that has lived on this planet. And yet, perhaps its greatest contribution cannot be measured by tides, climate, or even the length of the day. It can be found in the stories humanity has told beneath its light. For as civilization grew, the moon became far more than a gravitational companion. It became a guide, a calendar, a symbol, a destination, and without it, human history itself would have unfolded along a profoundly different path. By now, millions of years have passed in our thought experiment. Earth has continued its endless journey around the sun. Continents have shifted, coastlines have changed, countless species have evolved, while others have quietly disappeared into the fossil record. Yet before we look even farther into the future, it is worth returning to a question much closer to home. What would the loss of the moon mean? Not for the planet alone, but for us. For all of human history, the moon has been more than a celestial object. It has been one of humanity's oldest companions. Long before cities were built, before writing was invented, before agriculture transformed our ancestors from hunters into farmers, people looked upward and noticed something remarkable. Unlike the stars, which seemed fixed in their patterns, the moon changed. Night after night it grew. Then it shrank. It disappeared. And then, without fail, it returned. This repeating cycle became one of the first reliable measures of time. Long before mechanical clocks or printed calendars, many early societies counted the passing months by watching the changing face of the moon. In fact, the word month itself traces its origins to the moon's monthly cycle. Ancient civilizations across nearly every continent built calendars around its phases. The ancient Egyptians, although famous for their solar calendar, still observed lunar cycles for religious festivals. The Babylonians carefully recorded lunar months thousands of years ago. The Greeks, Chinese, Maya, indigenous cultures of the Americas, and countless others developed calendars in which the moon played a central role. Even today, many of the world's religious traditions continue to follow lunar or lunisolar calendars. Without the moon, those calendars would never have existed in the same form. Humanity would certainly have found other ways to measure time. The rising and setting of the sun provide an obvious daily rhythm. The changing seasons reveal the passing of the year. But the moon offered something unique. It divided the long journey between one season and the next into smaller, easily observed intervals. It gave structure to time itself. Imagine growing up beneath a sky where no bright object changes shape from night to night. There are still stars, there are still planets, but none displays the familiar rhythm that generations learned almost instinctively. The very language of time might have evolved differently. Navigation too would tell another story. For thousands of years, sailors crossed oceans guided by the heavens. During clear nights, experienced navigators read the stars with astonishing precision. Yet the moon also played an important role. Its position helped estimate time. Its light illuminated coastlines. Its predictable motion became another familiar landmark in the celestial landscape. Even after magnetic compasses became widespread, the moon remained a trusted companion for travelers. A moonless Earth would not make navigation impossible. Modern GPS satellites would still orbit the planet. Sophisticated instruments would continue guiding aircraft and ships. But for most of human history, every voyage would have unfolded beneath darker skies. Ironically, those darker skies would offer one unexpected advantage. Astronomy itself would become easier. Without bright moonlight washing across the heavens, every clear night would resemble the best nights currently enjoyed during the new moon. The Milky Way would shine with extraordinary brilliance. Faint galaxies would become easier to observe. Nebulae invisible under a full moon would appear with remarkable clarity. Professional observatories already avoid bright lunar nights whenever possible because moonlight reduces the visibility of faint celestial objects. On a permanently moonless Earth, astronomers would enjoy ideal observing conditions almost every night. Perhaps humanity would discover distant galaxies sooner. Perhaps the expansion of the universe would be measured earlier. Perhaps some of astronomy's greatest discoveries would arrive generations ahead of schedule. Yet something else would be lost. The moon has inspired curiosity in a way no other celestial object has. Unlike the distant stars, it appears close enough to touch. Its mountains and dark plains are visible even to the naked eye. Children naturally wonder what lies upon its surface. Poets imagine walking beneath its light. Scientists ask how it formed. Explorers dream of reaching it. In many ways, the moon became humanity's first destination beyond Earth. When the space age began in the 20th century, it was not Mars that first captured our footsteps. It was the moon. The Apollo missions represented far more than technological achievement. They transformed humanity's understanding of its place in the universe. For the first time, people walked upon another world. They looked back and saw Earth rising above a barren horizon, a fragile blue sphere suspended in endless darkness. Those photographs forever changed how we think about our planet. Without the moon, that chapter of history would never have been written. Human space exploration would still continue. Eventually, engineers might attempt missions directly to Mars or to asteroids. But the nearby proving ground that challenged and inspired an entire generation would simply not exist. The history of technology itself could unfold differently. Culture would change as well. It is difficult to imagine literature without the moon. For thousands of years, it has symbolized love, longing, mystery, solitude, hope, renewal, and the passage of time. Painters filled their canvases with moonlit landscapes. Composers wrote music inspired by its quiet beauty. Poets across civilizations compared its gentle light to memory, faithfulness, and distant dreams. Countless stories begin with a full moon rising over forests, mountains, or quiet seas. Languages around the world carry expressions shaped by its presence. Even modern films and novels continue drawing upon imagery that people understand instinctively because the moon has always been part of human experience. Without it, an entire dimension of culture would never emerge. Then there are eclipses. Among nature's most astonishing spectacles, total solar eclipses occur because of an extraordinary coincidence. The moon is about 400 times smaller than the sun. It is also about 400 times closer to Earth. These two relationships almost perfectly cancel one another, making both objects appear nearly the same size in our sky. The result is breathtaking. For a few brief minutes, the moon completely covers the sun. Day becomes twilight. Stars appear. The solar corona shines like a crown of white fire around the dark silhouette of the moon. Generations have traveled across continents simply to witness this rare alignment. Without the moon, no total solar eclipse would ever grace Earth's skies. Nor would there be lunar eclipses, when Earth's shadow slowly turns the moon a deep copper red. Entire branches of observational astronomy that advanced through eclipse studies would never exist. The sky itself would feel quieter, less dynamic, less personal. Perhaps that is the moon's greatest gift. It reminds us that the universe is not static. Night after night, its changing face reveals that the heavens are alive with motion. It invites questions. It rewards patience. It teaches that even the most familiar things are part of a larger cosmic dance. Remove the moon, and humanity loses far more than a source of light. We lose one of our oldest teachers. Yet one final mystery remains. Why did Earth possess such an extraordinary companion in the first place? Among the rocky planets of the solar system, our moon is remarkably large relative to the planet it orbits. Was this simply an accident of cosmic history? Or did the birth of the moon help make Earth the living world we know today? To answer that question, we must travel back, not forward, to the violent beginning of our planet, when a colossal collision may have created both the moon and the conditions that allowed life itself to flourish. As we reach the end of this journey, it is tempting to think of the moon as something Earth simply happened to acquire, a fortunate companion, a beautiful ornament hanging in the night sky. But modern planetary science tells a far more extraordinary story. The moon was not gently captured as Earth drifted through space, nor did the two worlds form independently before meeting by chance. Instead, nearly every line of evidence points toward a far more violent beginning. To understand why our planet has a moon at all, we must travel back more than 4.5 billion years to a time when the solar system itself was still under construction. The young sun had only recently ignited. Around it circled countless fragments of rock, metal, and ice, remnants of the cloud from which the solar system was born. These bodies repeatedly collided, merged, and shattered, slowly assembling the planets we recognize today. Earth was not yet the blue world we know. Its surface was a landscape of molten rock. Volcanoes erupted almost continuously. Asteroids struck with astonishing frequency. Entire oceans had not yet formed. The atmosphere, if it existed at all, bore little resemblance to the air we breathe today. It was a world in constant transformation. Then came one of the defining events in Earth's history. According to the giant impact hypothesis, the explanation supported by the greatest body of evidence, a young protoplanet roughly the size of Mars collided with the early Earth. Scientists have named this lost world Theia. The collision was almost beyond imagination. It was not a head-on impact that shattered both worlds completely. Instead, current models suggest a glancing collision occurring at tremendous speed. The energy released exceeded anything humanity has ever witnessed. Entire regions of both worlds were vaporized. Mountains of molten rock were hurled into orbit. For a brief period, Earth may have been surrounded by a glowing ring of debris, stretching thousands of kilometers into space. Over time, gravity began its patient work once again. Fragments collided, they merged, they grew larger, within perhaps only a few thousand years, a remarkably short time in astronomical terms. That orbiting debris assembled into a single new world. The moon was born. Although no human could ever witness such an event, its fingerprints remain visible today. Lunar rocks returned by the Apollo missions share striking chemical similarities with Earth's mantle. The proportions of many isotopes are almost identical, suggesting that Earth and the moon formed from the same material. At the same time, the moon contains relatively little iron compared with Earth, consistent with models in which much of Earth's heavy metallic core remained intact, while lighter material formed the moon. Over the past several decades, increasingly sophisticated computer simulations have strengthened this picture. Details continue to be refined. Researchers still debate the exact size of Theia, the angle of impact, and how rapidly the moon assembled. Yet the broader conclusion remains remarkably consistent. The moon is not a stranger to Earth. It is part of Earth. In a very real sense, our moon was born from our own planet. This realization transforms the question we have been asking throughout this documentary. Instead of asking what would happen if the moon disappeared overnight, we might ask something even more profound. What if the moon had never existed at all? The answer reaches far beyond the night sky. Without the giant impact, Earth itself might have become an entirely different world. Its rotation would almost certainly have been different. Its axial tilt may have evolved along another path. Its tides would have remained far weaker. The coastlines where land and sea met would have looked different from the very beginning. Some scientists have suggested that the moon's unusually powerful early tides may have played an indirect role in creating environments favorable for the emergence of life. As the young moon orbited much closer to Earth than it does today, tidal forces would have been dramatically stronger. Vast stretches of coastline would have flooded and drained repeatedly. Shallow pools could have concentrated organic molecules, exposing them to alternating cycles of drying and rehydration. Some researchers propose that such environments may have encouraged increasingly complex chemical reactions during the earliest stages of life's development. It is an intriguing idea, but one that remains a scientific hypothesis rather than an established fact. Life may well have emerged through other pathways. Hydrothermal vents, deep beneath the oceans, offer another compelling possibility. Subsurface environments protected from harsh radiation present still another. At present, scientists cannot say with certainty which environment gave rise to the first living cells. What we can say is that the moon profoundly influenced the young Earth from the earliest chapters of its history. Its gravity shaped coastlines. Its tides stirred the oceans. Its presence helped regulate the planet's long-term stability. Whether or not it was essential for the origin of life, it undoubtedly influenced the world in which life evolved. This realization has inspired one of the most fascinating discussions in modern planetary science. Astronomers have now discovered thousands of planets orbiting distant stars. Some resemble Earth in size. Others orbit within regions where liquid water might exist. Whenever a promising new world is found, scientists naturally ask whether it could support life. Increasingly, another question follows. Does it have a large moon? At present, detecting moons around distant planets remains extremely difficult. Only hints of possible exomoons have been observed. Yet many researchers wonder whether large moons might contribute to planetary stability in ways similar to Earth's. The answer remains unknown. Perhaps Earth is unusual. Perhaps many living worlds possess large moons. Or perhaps life proves adaptable enough that such companions are unnecessary. The universe has not yet revealed its full story. There is a certain humility in that uncertainty. Science does not become weaker by acknowledging unanswered questions. It becomes stronger. Every discovery opens the door to new mysteries. As we imagine a moonless Earth, we are reminded that the familiar world beneath our feet is the product of countless unlikely events unfolding across billions of years. A collision, a new moon, patient gravity, slowly lengthening days, steady seasons, living oceans, evolving ecosystems, curious minds looking upward. Remove any one chapter, and the story changes. Tonight, if you step outside after sunset, the moon will almost certainly still be there. It may appear as a thin crescent resting low above the horizon. Perhaps it will shine as a brilliant full moon, illuminating fields, forests, mountains, and oceans. Or perhaps it will be hidden beyond the horizon, waiting to rise later in the night. However it appears, it is easy to think of it as something ordinary, something permanent, something that simply belongs in the sky. Yet this quiet companion has been shaping our planet every hour of every day for more than 4 billion years. It has guided the tides without asking for attention. It has steadied Earth's slow dance through space without making a sound. It has illuminated the nights of every civilization that has ever existed. And perhaps that is the greatest lesson of this thought experiment. The forces that shape a world are often the ones we notice the least. The moon asks for nothing. It shines without speaking, yet through gravity alone, it has helped write the history of oceans, climates, living creatures, and human civilization itself. In the vast silence of space, Earth has never truly traveled alone.